Welcome to the Piezo SHOCK Show, episode number 57. Today I'm going to speak about how to automate what's the kind of basic process on automating the measurement of ultrasonic displacement using the visual methods that I explained earlier. And if we want to measure, we first have to calibrate the camera according to a known scale. This is kind of a messy 1mm scale here. And then we can take a blurred image of an ultrasonic tool vibrating. We can come up with some ratios and thereby derive the displacement. In this case, it was 43 microns. So I actually have one of these running right now. So what I have basically is a program called YawCam, which takes your webcam and it turns it into a image stream. So it's constantly sending images to a certain file. And then we have here our ultrasonic vibrating image. Now you may not think it's vibrating, but I can change the frequency and it'll stop. And I change the frequency. So I'll do something like this. I'll put that there, and I'll put this here, just so you can see that. And then start on, that's oscillation, and off, on, off, on, off, off, on, off. So in this way, you can come up with a displacement value. So this image here is being actually streamed to, okay, did not want to do that. It's being streamed to the LabVIEW program. So it takes the image as the first, it inputs the image, then it converts into black and white. Let me just zoom out for everybody. It converts the image into black and white. I do have something where I can rotate the image around this little rotation here. Then what I'm going to do, I'm going to choose a location that I would like to analyze. And in my program, I specifically hold a shift key, and then I click and I drag over that area. And I want to zoom in just to make sure I get a better value here and a better kind of block. So I'm going to do that again, shift, hold that. Actually, I'll start from, actually here is good. Hold it, click, hover over it. That gives me this blurred pattern, which gives me this histogram. And there are a couple of ways to find the value. So you can assume that these peaks are the peaks of the dots. Therefore, this gives us this value, 143 pixels. So let's just assume this is 0.4 for argument's purposes. Actually, let's do 0.30. Okay, so and then we have a couple of ways you can determine the differences between the pixels, like determine the two dots which are now causing separation. One of the methods is using manual, as I just showed. You can kind of highlight these cursors and get them on the locations, and obviously you wouldn't have the image continuously acquisition being made during that time, but you would stop it. So there's also this peak auto, which just takes the top two highest peaks, and there's some algorithm there in order to make sure you're not going to catch any other peaks happening here. And then there's another peak detect function in LabVIEW, which can also be used automatically to capture these peaks. So it looks for peaks in the data based on a certain width that you have provided here. So in this case, assuming 0.3 microns per pixel, we have a stroke length of 40 microns. And now, if we take the amplitude of the voltage, how high is it right now? It's pretty high. Let's do this. Okay, be better on the memory resources someday, but okay, let's do that so you can see kind of both. And I'm going to change frequency in order to get, let's say, a better so the stroke length is being calculated by the constant value. So now, like I changed the frequency, the histogram sort of shifted off its place. There seems to be some movement there, so I'll just get that other spot. Sometimes there is movement. This the specific transducer that the way I'm holding it's not really tight. So there's I got the histogram again. And last time it was 40 microns, and now it's going to be I changed that a little bit, and now we got 55 microns. And basically the peak algorithm is close to matching the manual version. And just making sure, I just want to make sure that we don't have, that we can track. Amplitude is easier just to alter and change. This to show the reduction. So I'm reducing the amplitude of voltage. So I want you all to take a look at this peak value, which is 180, because the manual is not going to show 180 pixels. So I'm reducing that. Now I've reduced the voltage, and now we got 162. So basically we are reducing. And it also points out another thing here. When you do these, you would ideally like to highlight a larger area, meaning up and down, so you can actually accommodate a little better for some shifts. Oops, that wasn't the best. Some selection problem here. There you go. So there we go. You have a little bit more. So I'm going to continue to reduce this value. And I'll reduce the voltage about half. Not half just quite yet. So the algorithm, just to map it, that would probably be the peak there, and that would probably be the peak there. So it is running a little bit wider, I would say. Well, actually it's 147, so we're good there. So as you keep decreasing this voltage value, so I'm decreasing it. Now we're kind of like all the way to 21 volts. And at this point, we have probably a peak there and a peak there. Now it kind of gets ambiguous when you get such a low stroke. But as you get higher, or you get actually a better signal in terms of your image, then that is going to produce a better final result. So if you want to take a look back at our image, we kind of don't really have much in the way there, but you may actually benefit from a different spot at that point. You have to play around with your camera and making sure that you're getting consistent. But usually once you have a consistent setup, you may have a special needle that or a tool that has a specific mark that makes it easy to distinguish and identify. But you typically don't want to be doing this method for very low displacements. So increasing the voltage once again. So I'm increasing the voltage, and now you're seeing this band get larger, and there's a little bit of movement on the device itself because it's not really held down very tightly. So that's obviously my fault there. Let's do that. All right. Give me the histogram again. and we are, let's just leave it at that voltage. That seems to be what we're going to capture. And now we're at 77 volts, and we're at 185 versus about 130. So it's not necessarily tracking voltage linearly, because as voltage increases, the resonant frequency shifts away, so you're not going to get as much for voltage, but current would more than likely kind of be similar. So current's 137 millivolts, and if we reduce the voltage about half, or seems like we mainly have, we just have a lower displacement there according to the voltage, and there's like capacitance that plays in, and actually it's lower voltage is actually getting more current. No, actually it's not. It's all relative here, which so yeah, that's the way to get this data automatically recorded. And I mean, once you have your number, your pixel value multiplied by a multiplier, then you'll be able to export that and analyze that in a frequency response plot. Let's see, let's clear this chart. Let me see if this part worked. So this is the stroke using the pixel peak algorithm multiplied by this. This is the stroke. So let's see. So if I increase the voltage a little bit, we're still good on the histogram. It still fits just fine. Then we've kind of increased the stroke level from 50 to 56. And in a similar way, when I've really reduced it, let's say, yeah, that still will work. That I think the algorithm would still catch that just fine. We have now reduced our stroke to 20, or our displacement to 20, and we actually increase it again. We kind of lost that there because this this thing is not actually, it's having trouble. Actually, it's not having trouble. Yeah, it's just it got that back. So yep, it seemed to have things skip some steps, so that's fine. But anyways, it got back to its original stroke at it says 1.1 millivolts into the amplifier, but that's 77 volts RMS, and 134 volts milliamps over the current sense resistor. Makes it about 132. Probably 13 milliamps RMS. So let's get back here. So I also am going to take a second and let me open the camera. This is show you the setup again, so you guys are familiar with what's happening. So we have our transducer right there. This is a little bit of a setup here, and this is our USB microscope. And that's all. It's kind of a pretty simple setup. But I think you'll find this topic inspiring. I'm going to be continuing to work on this project and release that soon once I feel it's mature enough for you all to use this program. But meanwhile, I just wanted to go over those concepts with you regarding the histogram, regarding how you can actually measure those displacement accurately. There are a bunch of programs that you can use to analyze this data, but yeah, the easiest way is obviously what I did here is visually kind of count those pixels using some draw program with the drawing tool. That's one way. There's also reticles that can be installed in stereo microscopes that can be used there. There's a couple of ways, but I just wanted to show you what I've been doing, what I've been working on. We can automate this process. All right, you've been watching episode number 57 Can you automate the measurement of ultrasonic displacement? Yes. So please check out the links in the description for the notes of this video, as well as links to get a better idea about my consulting offerings. I do consulting for ultrasonic transducer development, which does include a lot of measurements. I believe measurements are the key to understanding the transducer and then making informed decisions. Oftentimes we do end up not knowing what to measure or what's significant, because there's so many ways to do measurements, so many different types of equipment. It's hard to kind of get your mind wrapped around it completely. So you'd contact an expert like myself in order to get your project going and measure and get data. All right, so you've been watching the Piezo SHOCK Show. I will see you in the next video.